Now, the way we have classical mechanics, or what's generally known as Newtonian mechanics. In Newtonian mechanics, we have the basic differential equation in terms of Newton's second law of motion, and that equation is F is equal to ma, where m refers to the mass and a refers to the acceleration. Now, in similar way, when we go into the domain of matter waves, we have equations of motion, and we call these equations of motion as Schrodinger's wave equations. So the motivation here is to have that equation in its formal form. It doesn't need to be arrived to the result of this equation of motion, but we would like to take this trivial approach to obtain the equation of motion of these matter waves. And those equations of motion we call as Schrodinger's wave equations. And we have two kinds of equations of motion here. The first one is it is Schrodinger's time-independent wave equation. So Schrodinger's, it is Schrodinger's. What we have time independent wave equation. So, to arrive to the result of having this Schrodinger's wave equation, what we can start with is that the non-dissipation of the wave packet. We have the wave packet which does not dissipate. Uh, dissipate the non-dissipation that I'm trying to refer here is that we have a wave packet and we have particles somewhere in this wave packet, and this wave packet does not dissipate under certain circumstances, and uh, and this non-dissipation of electrons, say, revolving around the orbit, it can automatically be a consequence of obeying the Schrodinger's wave equation. And this Schrodinger's wave equation we are interested to derive here. Now, if I consider a system, I should say stationary wave, a system of stationary waves, and these waves are to be associated with the particle. And let me assume assume a function at psi of r and t. Now, this is what I will choose as the wave displacement for the de Broglie waves at any location of r equal to xi plus yj plus zk at some time t. Now, then the differential equation of this wave motion in 3 dimensions, in accordance with Maxwell's equations, can be written. We can write down in a very formal Maxwellian formulation. And how can we write this? It is del square psi, which is the function of position and time, is 1 by u square dou 2 psi by dou t2. Or for this this Laplacian operator, we can open this operator and we can write down it in a very formal way, like dou 2 psi upon dou x2 plus dou 2 psi upon dou y2 plus dou 2 psi upon dou z2 is 1 by u square dou 2 psi upon dou t2. So this is what we are trying. We're writing a function of what we call as the wave of displacement for the de Broglie's waves at some location r, and we can write down this in a very formal Maxwellian equation type like this. You can see it like this, where this u is the wave velocity, and this u that is here, this u is the wave velocity. So this u in this equation is wave velocity. That should be the case. Now, the solution of equation the solution of this equation that we have here, if I call it 1 for the time being, the solution of this equation gives me psi. It gives me psi as a periodic displacement. As a periodic displacement. All right. So, so what is that periodic displacement? Is psi of r, and t is psi naught of r e to the power of minus I omega t. Now, where this psi naught is nothing but the amplitude at the point we consider. It's the amplitude. All right. Now, it is a function of r. This psi, this amplitude is the function of r. It's the function of the coordinates r has x, y, and z in it. And it's not the function of time that this psi naught r I'm talking about. Now, this equation that we have here, it may be expressed in a formal way like the way it is there. So what we have is psi of r and t, and we have the amplitude of this wave, and we have an exponential function. And now, what is this? This is all the periodic displacement that we are writing here. Now, if I call this as equation 1, and I would like to differentiate this equation, and if I differentiate this equation with respect to time, so what am I going to get here is let me differentiate it like this is dou psi by dou t. So what I'll have here is this omega will come here. This will be minus I omega psi of r e to the power of minus I omega t. And I will differentiate it again with respect to time. What am I going to get is dou 2 psi by dou t2 is you will have iota square, and you will have finally you will have minus omega square psi of r and t. Okay, this will be the case here, and this equation that I have for the double derivative of psi with respect to time, I would like to substitute this thing in the very first equation that I have. So if I call this, this should be my second equation. This is my first equation. I will call this 3. So substituting this 3 in 1. So substituting this 3 in 1 is going to give me, okay, what I have is this Laplacian operator. I would like to write in that form. This is equal to, and for this double derivative of psi with respect to time is minus omega square psi of r and t. So here I will have minus omega square by u square psi of r and t. This should be the case. This should be the case here. And this psi is, we have the psi here and we have the psi here. And if we move on from here by defining this omega, as we know this omega is the angular frequency, so it is 2 pi nu. And we can write for this nu as 2 pi. Now nu is v by lambda. So what we have v here is u. It is u by lambda. Okay, so this u is the velocity, right? And it's already defined that this u is the velocity of the wave. So if we move from here, so what I have, so I can have omega by u equal to 2 pi by lambda. That should be the case. Now, omega by u is giving me 2 pi by lambda, so I can use this in this equation, right? And what will I obtain from here is, I may call this 4, I may call this 5. So substituting this 5 in 4, what am I going to get is psi minus times, this will be 2 pi by lambda whole square psi of r and t. Okay, this should be the case, and what can we expect from here is that this is plus, then this is 4 pi square by lambda square psi of psi is equal to 0. So far, we have not introduced we have not introduced the wave mechanical concept here, and so the treatment is general. It's a general treatment here. Now, for introducing the concept of wave mechanics, we must put from de Broglie equation, and what we have de Broglie equation is lambda is h by p, which we have already discussed. So making use of lambda here is taking us into the consideration of wave mechanical model. So this is my 4. So when I do so, what am I going to get is I'm going to get this del square psi plus 4 pi square m square v square by h square psi equals 0. All right. So now in this equation, what we would like to introduce is, suppose E is the total energy and V is the potential energy of the particle, right? And then the kinetic energy of this particle is simply the kinetic energy of this particle is simply E minus V, because the total energy will be K plus V. That should be the case, right? So this K is 1/2 of mv square, and this is what? This is simply E minus V. And if I write down something like this, m square v square by 2m is equal to E minus V, what am I going to get here is this m square v square is equal to 2m times E minus V. So I would like to substitute this mv whole square, what is purely momentum here. I would like to substitute for this 2m times E minus V. That should be the case, right? So I would like to call this say 5, and I would like to call this say 6. So what am I trying to do is I will be substituting 6 in 5. So when I do that, what am I going to get from here is I have del square psi plus I have 4 pi square by h square times 2m times E minus V of psi equal to 0. That should be the case, and we can have the del square psi plus, this is 8 pi square by h square m, okay, times E minus V of psi equals 0. Now this equation that we have arrived here, where you saw we took it from a very general differential equation, and what we did is we incorporated de Broglie wave into this equation, and this equation is called as Schrodinger's time independent equation, and the quantity psi is usually, it's generally known as wave function. And if in this equation I use h bar, and this h bar is h by 2 pi, so in that case, this equation, the Schrodinger's time independent equation, can be written as, this will be 2m by h bar square times E minus V of psi equals 0. So this is my Schrodinger's time independent wave equation. Right now, if I proceed from here, so this is my Schrodinger's time independent equation. Now the next step would be that I would like to have what's called as Schrodinger's time dependent wave equation. But before proceeding, if I boil down this equation, say for example for the free particle, now for free particle, that means there's no interaction involved, this potential energy should be equal to 0. So Schrodinger's wave equation for free particle would be square psi plus 2me psi by h bar square is equal to 0. Now, what should we aim at is we want the time dependent Schrodinger's wave equation. And to have that, what should we go with? We should go back to the equation that we wrote down as a solution of that differential equation. And if we rightly see that, what was that chosen as? It is here, psi of RT. So psi of RT is psi naught of R e to the power of minus I omega t. This is it. Now, I would like to differentiate this equation with respect to time. So differentiate with respect to time. So what am I going to get is the dou psi by dou t, and minus I omega t will be here, and you will be back with your original wave function. And what's that? That is psi. That should be the case, right? Now, this omega is, what's omega? It's 2 pi nu. We have for this omega as 2 pi nu. That should be correct from here. And if I go back to the postulate that E is equal to h nu, the Planck's equation, from here I have nu equal to E by h. Right? Now, if I do that, if I use that for this omega, I will have 2 pi. Instead of nu, I would like to have E by h. I would like to use this in this equation. So I will have dou psi by dou t is minus iota, 2 pi I E by h. So why I'm doubling this 2 pi, 2 pi I, 2 pi, doubling this. This is 2 pi E by h times psi. All right. So I can have this as the time derivative of the wave function. That is minus I times 2 pi by h dou psi by dou t. And I can write down this as, I can proceed from here. Okay, so this 2 pi by h is, it is basically h cross. It is 1 by h cross. So now what we have is, we have dou psi by dou t equal to, it's equal to what? It's equal to minus I, by h cross E psi. This is what we have. This is what we have obtained from here, and if we multiply and divide by I in this case, then we can bring down this iota will come into the denominator. So something might be missing here. No, that's right. This is minus. Now if I multiply it by iota and divide it by iota, so this is iota square, but that will be minus. So this will be E by h cross I h cross psi, and this is dou psi by dou t. That should be the case. Now I would like to substitute for this E psi, because from here I can have E psi equal to I h bar dou psi by dou t. That should be the case. Now, what would I like to do is that I would, if I go back to the Schrodinger's time dependent wave equation, which we developed right now, what's that? That is del square psi plus 2m by h cross square E. I will write it separate, then minus 2m by h cross square V. It has a psi with it, and it has a psi with it, is equal to 0. All right, that's the thing. So for E psi, I would like to use this. So what am I going to get is del square psi is equal to, let me keep this 2m by h bar square out. That will simplify my problem. So for E, this is I h bar dou psi by dou t. This is what we have, and then we have minus V psi. Let it be in the same way as it is. This is equal to 0. Now we can have the transformations, and I can have I h cross dou psi by dou t minus V of psi equals it equals h cross square by 2m del square psi. This should be the case. And uh, let me have this v on the other side, so that I come up with the formal way of writing Schrodinger's time-dependent wave equation. So here, what I can do is I can I can think of writing this as if I turn down it from the left side, this is minus h cross by 2m del square psi, and there I have minus v of psi equal to I h cross dou psi by dou t. What I did, yeah, I have to have something has gone fishy here. I'm not sure, but somewhere I might have lagged in terms of the signs. And what finally we will have here is here we will have plus, and here we will have plus. So this equation that is in front of us, this equation is called as time dependent Schrodinger's wave equation. And if I keep this psi out of it, this is minus h bar square by 2m del square plus v. If I keep psi out, is equal to I h cross dou psi by dou t. Now this whole thing is called as Hamiltonian. This whole thing is called as Hamiltonian, and it's represented by capital H. It's represented by capital H, and this is this whole thing here is the energy operator, and I can write down this Schrodinger's time-dependent wave equation in terms of Hamiltonian. So the equation that I can write is H psi is equal to E psi. Now this equation forms the Schrodinger's equation, and it describes the motion of non-relativistic material particles. This is the way we have Newtonian equations in classical mechanics. And in the similar way, we have Schrodinger's equation in quantum mechanics. And the equation that we have is the Schrodinger's time-dependent wave equation. And this equation is valid for those particles who have velocities very, very less than that of velocity of light.